afternoon, students. We'll start with our today's lecture. So in the last topic we had completed the safe and unsafe states. What are those conditions? So now we'll be going with the banker's algorithm for single resource. Now what is banker's algorithm? So basically we'll read here a scheduling algorithm that can avoid deadlocks due to Dijkstra 1965. It is known as Banker's algorithm and is an extension of deadlock detection algorithm. So Banker's algorithm is basically an extension algorithm for the deadlock detection algorithm, and which was a solution to avoid deadlocks from the Dijkstra deadlock problem in 1965. It is modeled on the way of a small town banker might deal with a group of customers to whom he has granted lines of credit. Years ago, bank did not lend money unless they knew could be repaid. What algorithm does it check to see if granting the request leads to an unsafe state? If so, the request is denied. If granting the request leads to a safe state, it is carried out. So it's just a basic comparison between a banker who is running that bank and the actual algorithm of deadlock. Means, suppose if I say that there's this bank is a small town bank, it's not a multinational or an international bank, it's a normal small town city bank in which that banker is lending money to the customers or a group of customers, that is in credit, means in a part of loan. And when he is lending that money in the part of loan, priorly it was like people used to, and they were given a certain duration to return it, and if they cannot return it, they won't be lended with the money. So likewise, what the algorithm checks here, if we compare this condition with the actual deadlock algorithm, what can be said? What the algorithm does is check to see if granting the request leads to an unsafe state. If the resource allocation is done to my process, if it is taking me to an unsafe state, then the request is denied, then the resources will be denied to that process, it will not be given. If granting the request leads to a safe state, means if they return me the same money, I can lend them the money again also. So it's giving me a safe condition, and that is the reason it is carried out further. So we see 4 customers A, B, C, D, each of whom have been granted a certain number of credit units. That is, we'll see here and then we'll compare it with the diagram. The banker knows that all customers will need their maximum credit immediately, so he has reserved only 10 units rather than 22 to service them. In this analogy, customers are processes, units are say tape drives, and banker is the operating system. So they have compared it likewise. The customers go about their respective businesses, making loan requests from time to time, that is asking for resources. At a certain moment, the situation is shown in figure 6.11. The state is safe because with 2 units left, the banker can delay any request except C's, thus letting C finish and release all 4 those resources. With 4 units in hand, the banker can let either D or B have the necessary units, and so on. So they have explained it in such a way that suppose if banker has who has to grant the units, that is the resources, my operating system has to grant the resources to my process, what it will do, the banker knows that all the customers need their maximum. If I say 10, I will use 10 obviously. So what the system is doing, system is telling me I have, no, I don't have 10, I have only 8. So you talk according to 8. So each 2 units each per person, that will keep in the safe state, that is in the safe zone, so that in future if it requires, it can take it out. So in this analogy, when we talk about customers, like with the banker's algorithm compared, customers here are processes, means they are provided with the resources. Units means they are tape drives, your normal, and banker is the actual operating system who is providing you the lending of money. So customers go out there, they customers will ask for resources, that is your operating system will ask for a resource time to time. At a certain moment, the situation is like the state is safe because only two units are left. So only two, if two units are only left, the banker can delay any of the request. So banker can delay, he'll say you have to wait because I do not have this much amount of resource, and will tell another person that you have four units with you of which your duration is to be completed. Complete your task faster and return those four units so that the duration he has given to the next one can be completed. So this is basically done with the help of this diagram, which is there, that he has actually resources assigned to those processes and resources still needed, the actual requirement of those resources with multiple resources at a time, not only single resource. When it comes to a multiple resource access, this can be done for. Next is, look for a row R whose unmet resource needs are all smaller than or equal to A. If no such row exists, system will eventually deadlock. So if units are not possible, it will ask for a resource from somebody else and it will get in a deadlock condition. Assume the process of row chosen request all resources needed and finished. Mark that processes are terminated. The process which get completed, mark them as terminated so that they do not create a confusion, and its resource to A vector. Repeat step 1 and 2 until either all processes are marked terminated, that is safe state, or no processes left whose resource needs to be can be made in the deadlock. So separate safe state processes resources as well as the deadlock condition processes. Next is again a main question which is asked frequently in the exams, that is write the steps or the conditions for deadlock prevention. So they look like same, but the explanation for your deadlock conditions to occur and preventions to occur is same, but the explanations are different. Again, assure at least one of these conditions never satisfy. So prevention and occurrence can be somewhere compared, means rather than occurring, if we use these steps that we try from all these four steps, any one of them will not get followed, we can try to stop deadlock prevention. And how can we do that deadlock prevention, we'll see here. The first one is mutual exclusion. Mutual exclusion means any of the process which is free, we can remove that resource, or we can, that is this condition ensures that resource should be used by single process at a time and it remains with using process is non-shareable mode. Any of the resource which a process is using, that process cannot directly share it to somebody else. He has to complete his task, release that resource, and then can share it to somebody else. Hold and wait. Hold and wait means until and unless somebody is working on that resource, another person has to wait remaining needed resources that at a present being held by other process. So even if I require that resource, I should know that somebody else is using that resource, so I have to wait in a hold and wait condition. Once that person completes or terminates the task, that resources will be given it to you. No preemption. Preemption of the resource will not be done. Process holding resource releases it on its own after the completion or of the chosen task. So until and unless, you cannot go and purposely take back the resources until and unless the process completes its task. Circular wait condition. Again, circular wait condition, if any of the resource dependencies is removed, circular wait condition will not occur. And out of all these four, if any one of them does not satisfy, means if I remove circular wait condition, then These three also cannot make a deadlock. All the four are required to make a deadlock, and to deadlock to happen, if any of the one condition is not there, deadlock will not happen, which is indirectly a deadlock prevention type. So deadlock prevention means from all these four steps, any one of if which does not satisfy, if we do not perform any one of these, if we try to hold on to any one of the type of out of these four, then deadlock will not occur. Attacking circular weight condition, what we can do is numerically ordered resources, a resource graph. What we can do is in the circular weight condition, we'll try to give it an extra resource so that it gets out of the circular weight condition, and dependencies of the circular weight conditions will be removed. Next is attacking circular weight conditions. What we can do is, what approaches we can take for prevention. If mutual exclusion is there, spool everything, means separate everything. Hold and wait, request all resources initially. Initially when they are starting the process only, give them separate resources. No preemption, take resources away. If they are not working on it, purposely take back it away so that other process can complete its task. Circular weight, order resources numerically. Even if they are in the circular weight condition, in the process when they have come, order them in a sequence so that circular weight condition can not occur in deadlock. Communication deadlocks, how do they occur? When you have host communications, and that is the reason you have a buffer, again you have a router, then your host is communicating, buffer is communicating with your host. So these are intercommunication deadlock situations also using networking. So this can also happen. The last is live lock. Live lock again is not actually your condition. Live lock is to check whether your problem has a solution or not, is called as the live lock. Live lock is basically not used nowadays because it's not actually applicable somewhere, but live lock has certain classes and these programs, that is, enter the region of deadlock with resource 1, with resource 2, use both the resources, leave the region with both the resources, and provide it to another class. Another class will also do the same functioning. Busy waiting, that can lead to live lock. Busy waiting means if you keep on continuously keep the resources waiting, it can cause a deadlock, and for which we can use a live lock condition to solve those problems. With this we have ended up with chapter 6. I'll be providing assignment for this chapter which you have to submit by today evening, that is 7 o'clock. Further, some topics of chapter 5, two topics are remaining, that is power management, and I guess two more topics are remaining, that also will complete by today. And all the attendance and the lectures which I have provided you today, you have to submit those attendance today by 7 o'clock only. After that I'll be submitting it to the college. So if you have seen those videos, please fill the attendance first and then download the videos to watch, as well as submit the assignments today before 7 p.m. when the assignment is provided. Thank you.